So Steve tells me he got his PhD from Imperial College, which is in London. Then came to Australia to work for Telstra Research Lab, which is one of these large labs, industrial labs that no longer exists, or is a shadow of its former self, no longer exists. He worked for some other companies and then started work at the Australian National University, which is in our beautiful but somewhat boring capital, Canberra. And so he has been working for the last many years on integrated optics, particularly involving chalcogenide, a highly nonlinear material, and he'll share some of his secrets and truths with us, if I'm not mistaken. Off you go, Steve.
Okay, thank you very much. It's a pleasure to be here, and I hope that today I'll be able to transfer to you some of the enthusiasm I have for this topic in nonlinear waveguide devices. Because over about the last 5 years at the ANU, we've gone from a situation where we were struggling to get things to work into a position now where we could really see some bright future for some of these devices. So, as Martin said, I'm actually at the Laser Physics Centre. So at the Laser Physics Centre in the Australian National University, yes, where our main mandate is working on materials and waveguide devices. So what am I going to talk about today? So first of all, I'm going to review a little the origin of nonlinear effects in materials, talk a little about why nonlinearities can be bad as well as good, review briefly the Chi2 based effects in materials, the characteristics and what sort of materials you might want to use. Same kind of thing for Chi3. Then look at some of the metrics and measures that people talk about with materials and effects and what limitations really exist. Look at some materials comparisons and then go on to talk basically about chip scale nonlinear devices from the materials fabrication and performance perspective. Now, it's a very big field, so I'm not going to explore everything here. I'm really going to limit the discussions mainly to planar waveguide systems. I'm not going to delve deeply into the theory of the nonlinear effects, just talk more about phenomenological based explanations. And mostly the focus will be on third order effects in glassy semiconductor materials because they're the things that in kudos we spend most of our time working on. Okay, let's start out with the physical origin of nonlinear effects. So there is no one single mechanism that gives rise to nonlinear effects. There are actually quite a number of ways that you can obtain an optical nonlinear effect out of a material. However, those that are most interesting are usually based on electron-mediated effects because we all know electrons are very light, so you can move them around very fast. And that means that we can get high-speed effects. Now, in glasses, we usually get these effects out of induced dipole moments. And how do these come about? So here's a sort of representative diagram of a bunch of atoms sitting in a material somewhere at rest. No optical fields applied. The electrons are sort of just floating around, the nucleus is there, everything's uniform. Pretty uninteresting. Come along and apply a large electric field to things, and we're able to distort the electron cloud and create a dipole moment that then produces a polarization moment over here, which is basically the number of dipole moments in the material. And this is where we're actually able to get the nonlinear effect from. Taking it back to Maxwell's equations, the relevant part of Maxwell's equations arises out of the displacement here, which has a term for the polarization in it. And the normal practice is to expand that up as a Taylor series. So you get something like this, where we have these chi terms that go off to very high order. I think we saw some, just in the previous talk, some quite high order effects. The ones we're usually interested in are chi2 and chi3. Chi2 has an electric field squared term, chi3 has an electric field cubed term. Generally speaking, these chi's are pretty nasty quantities. To give you an example, chi3 in the most general case, is a fourth rank tensor with 81 elements. Each of those 81 elements is composed of 46 terms. So trying to figure out if you take some model of a material, what you're going to get up here is a very non-trivial task. So generally there are symmetries and other things that can reduce the number of elements, but even with that in Chi3, for any symmetry, there can still be a lot of elements in that tensor. That said, we usually have an electric field that's a combination of a number of different frequencies and maybe even DC terms that gets plugged into this equation. And it's the presence of these e to the n terms that gives us the nonlinear effect. So for example, taking the square term, as you probably heard from Martin the other day, if we were to put in a single frequency, then we get from e squared, we get 1 minus cos 2 omega t, i.e. second harmonic generation, ditto third harmonic, etc., etc. Now, next question is, so we've got a plethora of materials out there. How do we make any informed choice about which ones are likely to be more nonlinear than others? And it turns out that there are actually some measurable things that you can look at that give you some information about nonlinearity. It's a bit of a woolly measure, but you can still get an overall trend. So first thing you can look at is whether the nonlinearity is resonant or not. And we'll talk in a moment about what that means. The second thing that you can look at is the actual linear refractive index of a material if it's non-resonant. And again, in a moment, we'll see why that is. Turns out that in general terms, the band gap, the optical band gap of the material is a more useful predictor of what goes on for third-order nonlinear effects. But at the end of the day, despite all this kind of stuff, there is still a fair amount of woolliness in what number you're going to get, because there are various structural or material factors that mean any model that you apply is always going to have a margin of error of somewhere between about 2 and 5 times, depending on exactly what's going on in the material, for materials that have similar band gaps. Now, as I just mentioned before, for Chi3, it can be extremely complicated to come up with a number for that, and so modelling some of these materials to predict what kind of structure or chemical bond structure you might want to put in a material to get high nonlinearity is a pretty complex business. That said, for second order effects, there's been a lot of work done on that, particularly in polymers, that is really starting to bear some fruit now, and you'll get a very brief glimpse of that a little bit later on. But I think for Chi3 it's proving to be a lot harder. Okay, what's a resonant versus a non-resonant material? So basically here we're talking about a case where the pump light energy that we're putting into the material is close to some optical transition of the material. Most usually, this is the band gap in a semiconductor or a glassy type material. So when we get to this point, what's basically happening is that we're exciting resonant transitions up and down in the material, and you can get a nice big nonlinearity. The snag is you also get quite a lot of absorption. And as you'll see later, that's not a very desirable thing. In some cases, you can get around that, particularly, for example, if you look at the sort of work people have been doing in semiconductor and optical amplifiers. You've actually got a gain medium there. So you can actually overcome some of this loss by pumping the material and generating a gain. But there are still issues from that. Also, in the resonant state, you've got a potentially lower speed because you're talking about a system with energy storage. And in semiconductors, you've also got factors like the free carrier lifetime and carrier heating effects as well. In transparent glassy type materials, you've got a different situation in that it's non-resonant. And as I said before, you're talking here only about moving electrons around with an optical field. And so you can get very, very fast effects, femtosecond timescales apply basically. So on to the first of the sort of measures, if you like, of nonlinearity. A gentleman by the name of Miller went away, I think it was in the 60s, and did a lot of work looking at this and came out with a surprisingly accurate expression to predict the size of Chi2 nonlinearity based on an anharmonic oscillator model. And it's a very simple expression, it's just the product of the chi's, essentially. And this went on to be generalized to a somewhat less accurate prediction for Chi3, which is essentially the same thing, but with all 4 frequencies that are involved. What's interesting about this is that chi1 is proportional to the refractive index through this relationship. So you can go away and plot this as a function of refractive index. Here it is log n squared minus 1 on the bottom, log chi3 up here. You can see you've got pretty much a straight line with full line slope of 4. So this is now where you can start to see in here this scatter around this line, which is this factor of 2 to 5 that I was talking about before. But nonetheless, first order guide says that if you've got a high refractive index material, it's likely to have a high chi3. However, that's not by any stretch the end of the story. Linear refractive index is basically dictated by where the band gap of the material is and by what absorptions there are in the material through the Kramers-Kronig relationship. So when you look at nonlinear effects, you'll find that there are several types of nonlinear absorptions as well. You have your first absorption where you have the photon energy is equal to half the band gap energy. So there are 2 photons can pump a state up and you get an absorption into the band gap. Same thing at 3 photons, etc., etc., etc. So there you're looking at a system now that has a number of absorptions in it. And again, from Kramers-Kronig, that implies that there's some kind of dispersion relationship for the nonlinear coefficients. Perhaps the best known of these in the nonlinear space is the so-called Shaker-Bahai model. And they were basically exploiting a parabolic band gap band model of a semiconductor to try and predict this dependence on band gap, to try and figure out what goes on with different materials. So they went away and they did their modelling, and they came up with something that looks like this. So plotted up the side here is a normalised measure of the nonlinearity at some frequency, and plotted on here are all a bunch of different materials. This solid curve, I think, is the curve for a crystalline semiconductor. The dashed curve is for a amorphous semiconductor. And you can see that, broadly speaking, again, everything does follow this functional dependence. Again, you've got this kind of factor of 2 creeping in that you just don't seem to be able to get away from. Plotted another way, get a large log scale for a wide range of materials. Even some of the glassy materials down here actually seem to follow this dependence quite well. In our own work, we've gone away and done this with chalcogenide glasses, and lo and behold, it works for them too. And in this case, these are very definitely not simple 2-band materials. So that's kind of where it's coming from. Why should we really be all that interested in it? First thing about nonlinearity, is it good or is it bad? I think that's really a perspective issue. Depends on whether you're coming from the high data speed transmission camp or whether you're coming from the optical processing camp. Turns out that for long distance data transmission, with the exception of soliton systems where you're using the nonlinear effect to balance the dispersion of the fibre link, that nonlinearity is pretty much universally bad. There's a range of effects that do quite nasty things to transmission systems. First of all, we'll go through all these effects later, but self-phase modulation results in broadening of the pulses, narrowing of the pulse, broadening of the spectrum, closing of the eye, and jitter on the system. Crossphase modulation between different channels in a multi-channel transmission system has similar kinds of effects, and even goes further to produce phase noise to amplitude noise conversion. We have 4-wave mixing, where you can generate light that overlays existing channels, and also, in fact, mix in amplified spontaneous emission out of the system. And in fact, even within a single bit stream, the presence of dispersion will smear and differentially delay the frequency components of adjacent pulses, so you can then get mixing between those frequency components out of 2 different pulses that produces intersymbol distortion, intersymbol interference, beg your pardon. And lastly, we've got Raman gain type effects, which produce interchannel crosstalk and also transfer the energy out of the shorter wavelength channels to the longer wavelength channels, thereby degrading the signal-to-noise ratio of the shorter wavelength channels, causing them to fail in the link. So there's a lot of things there that are really not entirely desirable. However, nonlinearity is also good for us in the sense that we can actually exploit some of this and get an upside, even for curing some of these problems, and you'll hear about that from Mark Pelusi tomorrow as to how you can overcome some of these issues using nonlinearity in your favour. But aside from that, there is another upside. The other aspect of nonlinearity is that it's ultra fast in the right sorts of materials and way, way beyond what you can do with electronic speeds, electronic components. To my knowledge, the fastest electronics that anybody's made on a serious scale is an amplifier that has about 340 gigahertz bandwidth and 20 dB again. So that's, you might say, step response is coming up close somewhere towards, I don't know, maybe it's getting towards the terahertz rate, but you've still got several orders of magnitude on that with femtosecond speed you can get out of optical nonlinearity. So we can use that for ultra-high bitrate transmission and also ultra-fast optical processing of various sorts. Some of the things that are interesting, we can look at doing format-independent wavelength translation, which has plenty of network-type applications. As I just mentioned before, we can look at doing distortion compensation via phase conjugation in nonlinear materials. And as you'll hear from Mark tomorrow, that works pretty well. We can look at also ultra-broadband signal analysis. One of the things that's going on in Kudos is to make spectrum analyzers that have terahertz bandwidth, which is quite an interesting and useful thing as well. We can also use nonlinear effects for generating light, and indeed, somebody asked about OCT, was talking about OCT a few moments ago. We can make super wideband light sources using nonlinear effects. And we can also make wideband tunable sources that span very large tuning ranges. And lastly, we can also, as you probably heard earlier on, make ultra-short pulses and do a lot of different things with them. So nonlinearity does have a good upside that can be very useful in some settings. So let's go on now and start looking at some of the nonlinear effects that are out there, starting off with the second-order ones. So there's a range of interesting effects that are useful to us. Principally, these are the most common ones. Second harmonic generation, I think Martin dealt with in some detail. Difference frequency generation, which also includes a phase conjugation component. The electro-optic effect's not really a nonlinear optical effect, but it's very broadly used and it's a Chi-2 effect. And the sort of optical parametric processes are also widely used in laser systems today and for a lot of other things. Now, I'm sure Martin informed you that in order to get a Chi-2 effect, you need a non-inversion symmetric material. And generally, most people think of those as being crystals. And yep, that's where the bulk of the effort has gone. But there is a caveat to that. There is a way to overcome this non-inversion symmetric effect in glasses, polymer materials, a number of other things. We'll touch on that in a little while. So what are we talking about now? We're looking basically at this Chi-2 component here. And we're going to throw in a whole range of different frequencies and maybe DC fields as well. So if we take the simplest example where we just put in our two different frequencies, then if we expand this term z squared, we come out with this set of things here. So we've got a second harmonic term for the first frequency, second harmonic term for the second frequency. We've also got a sum frequency generation process, which in this instance is going to, if this was really red and green, and push this deep into the UV. The difference frequency generation that pushes everything out into the infrared, and this DC rectification term as well. And in particular, this term here gives us a lot of scope for doing some interesting things. We can configure it in quite a number of different ways. So this is the classic difference in frequency generation, which is often also referred to as parametric down conversion. Put in two frequencies, generate a frequency that's the difference of them. This is widely used in lithium niobate materials for wavelength translation and phase conjugation. There are some catches associated with that, but nonetheless there's been some quite impressive results generated with this. Next way you can configure it is an optical parametric generation, where we fire in one frequency, generate two new ones. This is very commonly used, as no doubt many of you know, in tunable laser type systems. We can also make an optical parametric amplifier using the same kind of idea, where we put in a strong pump, a weak signal, and use the parametric process to transfer the strong pump onto the original signal. So you're making a non-linear amplifier here. And there are some advantages to that in terms of being able to overcome spontaneous emission type effects. And lastly, we can do the same kind of thing, put it in a cavity to make an oscillator. So up here, our main interest is in wavelength conversion and phase conjugation. Over here in making tunable sources and wavelength converters, nonlinear amplifiers here, and tunable type pulse, typically pulse sources, but not exclusively pulse sources down here. Now, one thing we haven't talked about so far is phase matching, which is the necessity of actually keeping the phases of the various waves that are involved in these processes synced together so that we can hopefully attain exponential growth in the new frequency that we're trying to generate. Now, typically, this is achieved by manipulating the crystal axes to the crystal axes and the birefringence to match everything up and keep it all going along nicely. However, if we're talking about waveguide devices, that's a bit problematic because there aren't too many ways that you can easily exploit that due to the issues in crystal planes and other things when you want to actually turn it into a finished device. So there's another range of possibilities based on quasiphase matching, QPM, that can also work quite well. The typical method for doing this is actually to take a lump of your nonlinear material and invert some of the domains so that you've got the opposite sign of phase accumulation. So what we're talking about here is the case for a perfect phase match material, nice exponential growth. When it's not phase matched, you get this kind of periodic effect. So what we do here is we invert the sign of chi2 in the material pretty much around about the peak here. So at this next period of the phase match part is turned around and actually adds to the growth, and you keep doing that through the material, and you can get quite respectable performance out of that. The other way of dealing with this is to provide what's effectively a discrete lumped phase compensation based on a grating. And this is used, for example, to do quasi-phase matching in poled glass devices, again, reasonably successfully. But there is actually a third option as well. And for some applications, you actually don't need to generate this new frequency inside a waveguide. And an example of this, for example, would be pulse metrology, where what you want to do is bring either one or two copies of a pulse together, collide them inside a nonlinear material, usually to generate the second harmonic, and then image that second harmonic to get the autocorrelation, and if you frequency resolve it as well, the phase of the pulse. So when you're doing that, you don't have to capture this generated radiation into a waveguide. And that means that we can start to look into some more and alternative ways of generating the second harmonic, of which probably the most interesting is the so-called random domain materials. So this is a lot of work that's being done actually at the ANU by Wisław Krolakowski, and his main focus has been on strontium barium niobate, which he uses in an unpoled state. So what happens here is we've got domains that have inverted inverted chi2s, and domains that have a range of sizes. So the impact of this is that we've got a whole pool of grating phase match vectors in the xy plane. So if we now plough in a beam to the side of this thing, we can find a direction, every direction can find a grating vector that produces phase matching, and you'll get a sheet of light emitted in the plane of the device. This certainly isn't as efficient as some of the other methods, but for things like pulse metrology, efficiency is not so important. If we come in through the other direction, we have the same sort of thing going on, that we can always find a particular grating vector up here to produce phase matching. We get a cone emission out this direction of the light. Why is this interesting? Well, the big thing about this is that we can find phase matching at any wavelength, so that the second harmonic generation we can get out of this system is limited only by the material transparency. And I think Wisław has results that run from like 400 to 1700 nanometers, It's just we haven't been able to go any further because we don't have suitable sources and detectors. So they've also taken this concept and demonstrated autocorrelation measurement of pulses and, in fact, full phase retrieval as well. So it's quite an interesting method for metrology-type applications. I mentioned before that there is a way to break this inversion symmetry requirement because in glasses and polymers that are typically very nice waveguide materials, you typically don't get any chi2. And the way you do this is to make use, in fact, of the chi3. If you remember in the polarization equation, we had this term here, which we can rewrite as a chi3 times an EDC times E squared, which we can then replace this as an effective chi2. So what we're trying to accomplish here is to put in the material some kind of built-in field. And there are a number of different approaches to doing this. The classic, well, in fact, the very first method was actually based on high-power laser irradiation. The whole effect was in fact discovered when someone was ploughing a high-power Ti-sapphire laser down a piece of standard fibre. And they came back after lunch and blue light was pouring out the end of it, which was a bit of a surprise. And what was going on there was basically laser-based pollen. You can also, a few years later, somebody also realised that you can, for example, take a slab of glass or a fibre, heat it up to typically 280 degrees and apply a few kilovolts across it. What happens is you cause the impurity ions in the glass to drift. And by creating a charge separation, you create an electric field. If that electric field is applied across the core of the material, hey presto, we've got this term here and this term here. One can also use ionizing radiation. You can actually just directly implant charges in the material with electron irradiation or ion beam irradiation. And you can do a variety of summation of these different methods to hopefully attain the same thing. So in glasses, we're trying to engineer in an electric field. And I should add that this isn't only about ion drift. It turns out that in fact there are a number of other effects going on. If you apply enough electric field, you can actually create dipoles in the glass. You can also get to a stage where you start to create nanocrystallization. And of course, as soon as you've got crystals, you've broken the inversion symmetry as well. So there's still a lot of research going on trying to understand these effects, particularly in glasses. In polymers, you often have dipole moments in the polymer itself, but when you spin coat the polymer, they're all randomly aligned. So by applying high voltages to polymers with a bit of heat, you can actually start to align those dipole moments and get second-order effects. And the key thing about this is that we can now use non-crystalline materials to make waveguide devices, and that vastly opens up the range of materials we can consider using, because crystals are not the nicest thing to work with when you're trying to make wafers, large wafers, full of material devices. So second-order materials, there's a range of different materials. Perhaps the best known of all is lithium niobate, and that's the benchmark material. There's a wide range of devices commercially available in lithium niobate. It has an R33 of about 32 picometers per volt at 1550. So that's the benchmark against which most things are measured. So gallium arsenide has a somewhat larger chi2. Strontium barium niobate, which we talked about before, is even larger. Now I talked about polling and polymers. There's now a commercially available product from Gig Optics, which is a 100 gigahertz electro-optic modulator, and that has a Bellcore or Telcordia reliability tested R33 of about 80 picometers per volt, which is pretty respectable, really. The best anyone's ever done so far in a polymer is 450, and the belief is that within a year to 2 years, that's going to be 1,000. So we're really starting to go places with this, largely as a result of applying supercomputers and a lot of modelling to figure out what really drives this. In glassy materials, there are some options as well. This is a very particular chalcogenide glass, potassium phosphorus selenide. Even in the glassy form, it maintains a second-order effect, even though it's amorphous. This is basically down to the fact that it's nanoscale phase separated and has structures within that that are non-centrosymmetric. One can also take a truly amorphous glass and pole it. And currently the two leading contenders for getting sizable chi3s Chi2s, a telluride glass and chalcogenide glass. In telluride, the record at the moment is about 3 picometers a volt. Not too impressive compared to this, but what you need to realise is that in silica, which has a Chi3 typically 30 times less than telluride, they can get 1 picometer per volt. So the induced Chi2 is proportional to the Chi3, so you've got 30 times more Chi3 to play with. You should be able to get up to these levels with telluride glass, so this is an ongoing field of research to do that. With chalcogenide glasses, you're talking about 1,000 times silica, so we should be able to comfortably exceed this, but there's a lot of challenges in understanding how to apply a large internal electric field to these materials. It's a non-trivial exercise. Life isn't only about the size of this though, there's a range of other important issues that you need to think about. What's the transparency window? If you want to make something in the mid-infrared, polymers often aren't too good, for example. What's the absorption? This is one of the things that's been limiting a lot of the polymer materials, is even these sorts of materials have absorptions of 1 to 2 dB per centimetre at 1550 nanometers. How stable is the poling that you've applied in case of some of these? Again, that's another interesting challenge. There are results out there, such as this gig optics in a polymer, that show good stability. The interesting thing about this material is as it ages, it actually gets better. That must be one of the few materials I've ever seen that does that. In glasses, the charge separation issue, you can get diffusion, or you can, of the charges, or you can also get actually diffusion of protons into the material to neutralise some of the charge. But again, a lot of work's been done on that, and there are silica-based modulators that have been shown to be stable for 15 years or something. So, you know, there's a fair prospect of being able to achieve a stable poling for those. Damage threshold, another big one. A lot of these processes, we want to plough in a lot of optical power. Interesting questions of just how much power some of these will take, particularly the polymer materials. Phase matching is another one. Despite this large number up here for gallium arsenide, there's been a lot of trouble in being able to phase match it for some of these processes. And then lastly, from our perspective of making waveguides, can you actually make waveguides out of some of these materials? Clearly some of them, like polymers and glasses, you can. Gallium arsenide, certainly. Lithium niobate, there's been a lot of work on making waveguides there by diffusion into the lithium niobate. It is very challenging to make small core waveguide devices with tight bend radii and get a high integration density. So there are still issues with that. SBN, that's very challenging. So, you know, there's a lot of things that one needs to consider here. Okay, on to third order effects now. So now we're dealing with this term here. Again, if we take a single frequency case, we can actually collapse this a little more. Noting that our Chi1 term times the electric field is basically, in this instance, equal to the refractive index, then we can collapse Chi3 down through this process to an effective N2 to get an intensity-dependent refractive index. This is, for us at least, a key effect that drives much of what we do here inside Kudos. It gives rise to a whole range of effects that are of a lot of interest to us, such as the straight intensity-dependent index change, which we can exploit to do all optical switching. We can get self-phase modulation, which we'll explore in a moment. And, for example, one of the things that we're trying to do with that is make an all-optical data generator. We can do crossphase modulation, which for us, again, is all about making time division demultiplexers with. The same sort of thing with four-wave mixing. We can get the Raman effect, which is of interest for us for nonlinear amplification. And we can do super continuum generation to make very broadband sources. Importantly, these third-order effects, unlike the second-order effects, are present in all materials because there's no inversion symmetry requirement. So we can get a third-order effect out of any material. It's only a question of how big and how fast is it. For us, the most relevant materials are glasses and semiconductors. So taking the first of those effects, the intensity-dependent refractive index change, as I said, the key interest for us is in all optical switching here. So what you're doing in this instance is using that nonlinear induced refractive index change to get a phase shift. which we use typically inside either a Mach-Zehnder interferometer or a directional coupler to attain a switching action. So the first instance is a directional coupler. So we start off with what would be termed a 100% coupler, where at low power the light goes in here, couples across evanescently and comes out the other port. Nothing too interesting happens there. However, when we plough high intensity into this nonlinear waveguide device, what happens is that we get phase shifts inside here that decouple the two supermodes in here, so the light now stays inside this port, and we get switching of the pulse from this port to this port. In the Mach-Zehnder type device, we have a Mach-Zehnder here between these two pairs of couplers. We put another couple of couplers in here. This one's for injecting pump light, this one's for balancing the loss. And we have a nonlinear section in here. So fire a CW source in here. At low power, CW source comes out this port if the interferometer is balanced, and there's nothing coming out here. At high power, we get a nonlinear phase shift in this arm, and if that's pi by 2, then what we do is switch the CW source out to this port here, and we get a pulse. The minimum requirement to do this is pi by 2 phase shift. Some devices, like the coupler, actually need more than that. Next effect in the bank is self-phase modulation. So again, here we're making use of the nonlinear induced refractive index change, which, of course, here's the pulse. The index change follows the pulse amplitude. So now we've got a time-varying refractive index that varies across the duration of the pulse. Well, that's equivalent to a phase shift, of course. So now we have a pulse with a phase shift. And if you apply a Fourier transform relationship to that, you start to find for no phase shift, there's the spectrum of the original pulse. And as we increase the phase shift, you can see we start to grow different lobes, new frequencies, and broadening of the spectrum. And you can actually get very, very large broadening out of this with sufficiently high powers. You can also think of this phase shift as inducing a frequency chirp as well, which is a nicer way to think about it when you start to come into crossphase modulation. And this basically acts the same way as self-phase modulation. The source of the index change here is in fact another wavelength channel of data. So here we've got two channels of data. This top channel goes through a transition where you've got two ones on this channel, and you get frequency chirps off the edge of this pulse that with dispersion lead to glitches in the side of this pulse here a little further down the transmission link. So now you've just added a load of noise to your waveform, and detection is going to be harder at the other end of the link. Four-wave mixing, another interesting and useful process. So this is a process that, by its name, implies 4 photons are involved. We take 2 photons, annihilate them, and make 2 new ones. So we've got 1 photon here, a second photon here, and then they generate 2 different frequency photons. Conservation of energy and momentum puts some boundaries on what you can do with this. In that the sum of these energies has to be equal to the sum of these energies. So if you go away and rearrange that, you'll find that it means that these spacings here are equal to this spacing. So the frequencies that you generate are fixed by the spacing of these 2 wavelengths. There's also a momentum conservation relationship, which is just another term for phase matching. And if you, in the absence of loss, it reduces to the same phase matching criterion that Martin no doubt gave you yesterday. Raman, that's another useful effect that's completely different origin. But basically what happens with Raman is when you pump high powers into a material, maybe like 1 in a million photons will actually stimulate a bond vibration in the material matrix. And you can think of this process as an absorption and re-emission process, where you absorb a pump photon and then you re-emit it with lower energy. And the energy that's taken away is going into making this bond over here vibrate. So what happens is that you pump in a lot of light and you get out some proportion of that light at a lower frequency or a longer wavelength. And that's, the longer wavelength term is usually termed Stokes term. However, you can also, in a statistically lower number of cases, get the case where you put your photon in, it encounters a bond that's already vibrating, quenches that bond and picks up the energy and says thank you very much for that, and comes out at a higher frequency, and that's the so-called anti-Stokes radiation. However, that is a probably a couple of orders of magnitude lower probability, so your anti-Stokes generally tends to be much weaker than your Stokes. Now, in a glass, which this is some rough schematic diagram of part of the glass matrix, with a lot of different bond configurations, you have a lot of different bond angles. You can have, in this case here, you've got, if this was silicon here and oxygen here, you've got a bridging oxygen here rather than in the normal configuration here where it bonds to silicon on either side. You get strain in glasses as well, which changes the bond frequency, vibration frequency. So there's a lot of different environments for individual bonds in a glass, and hence you get quite broadband effects out of this. It's not a nice, sharp, single bond resonance, as it would be in a crystal like silicon, for example, where you get a very sharp Raman peak. And in silica, this Raman gain function is at 120 nanometers wide. So it's quite a broad effect that applies over quite a large wavelength range. Lastly, supercontinuum generation. Now, this is actually a hideously complex phenomenon that generates a broadband spectrum, ideally from a very narrow, short pulse. And it actually involves all the other effects that we've talked about previously in varying degrees depending on the pulse length, the length of the device, and a range of other things. Usually, the way to get the best supercontinuum is to use an anomalous dispersion waveguide, because then you can start to exploit soliton effects. And if you put something like 100 femtosecond pulse into an anomalous dispersion waveguide, you get soliton compression and finally soliton fission. So you start to generate new solitons, each of which has a broad bandwidth. Then you can start to get Raman effects, four-wave mixing effects, which amplify and generate new frequencies as you go down the material, and you just keep spreading the spectrum out. There are limits to how far you can go, but in a properly designed system, it's pretty wide. As an example of that, this is the supercontinuum generated in an 8mm long piece of tellurite microstructured fibre. It's engineered to have a dispersion zero just the other side of 1550 and uses a 1550 pump. And you can see that it's generated supercontinuum from about 700 nanometers out to close to 5.5 microns, which is pretty impressive. This is a plot here that shows the evolution of a pulse launched into an anomalous dispersion waveguide. You can see this is the spectrum. So the fact the spectrum is getting wider means that the pulse is compressing. You get somewhere down here, it fissions, and then everything takes off and the spectrum blows out. There are various dispersion effects and loss effects that limit how wide this can be. And over here you can see a picture of a supercontinuum in a reasonably long length of fibre. So here the light was launched. On my screen here, at least, I can see red light coming out here, which goes into this coil of fibre and gradually upshifts to blue light, just as the spectrum broadens. Okay, that's the range of effects we've got to play with. What goes on in real materials? What measures of excellence do we have for these materials? One of the key measures, as we talked about before, was linear absorption, and one defines an effective length based on the absorption like this. And what we want here is we want the effective absorption length here to be much, much longer than the length of waveguide that we require to get a high phase shift in the material. So that means that then we can get larger and larger phase shifts simply by making the waveguide longer. Whereas if we are loss limited, we're stuck. There's also a phase matching type of requirement that one can define a dispersion length as the square of the pulse length over this lot. And again, we're in a situation here where we want ideally the dispersion length, again, to be much longer than the length required for pi phase shift. There's another measure as well, based on walk-off. If you're using a multi-wavelength process, you don't want the pulses to walk past each other in the material, so there are walk-off based criteria as well, which also depend on the material dispersion. Then, of course, we talked about multi-photon effects earlier on. The one that's in most Chi-3 materials of interest is two-photon absorption. There's a figure of merit described as the nonlinear refractive index over twice the two-photon absorption coefficient times the wavelength. What's going on here? This coefficient is basically saying that if you're less than about 1 what starts to happen is as you increase the power in your device, the absorption, the nonlinear absorption starts going up, and you get into a regime where your phase shift starts to saturate. It doesn't matter how much power you plough in, you can't get any more phase shift. So the figure of merit of 1 is the magic number there that you'd like to be above. Also, there's a number of other things that are quite important. One of the classic errors, in inverted commas, that you see when people measure third order effects is to use a high repetition rate laser with high pulse energies. And what happens there is if there's any material absorption at all, then you actually start to heat the material. And in most materials, the thermo-optic effect is far, far bigger than the nonlinear effect. So if you're making say an all-optical switch with a Mach Zehnder, you have to be careful that you don't have a lot of absorption, otherwise you will be seeing thermo-optic switching instead of nonlinear switching. There are also issues related there with thermal effects due to damage, and higher order absorptions, index saturation are also all factors for which figures of merit exist. Limitations on what you can do here come from multi-photon absorptions. So the higher you push the power, then the more likely it is that you're going to get higher order multi-photon absorptions. And in terms of generating phase shift, that's bad. But for some people, like those who like to use femtosecond lasers to make waveguides, it's a great thing. Plow enough power into a transparent material and get 3 or 4 photon absorption, you can start to do all sorts of things with the material. There are also higher order nonlinear effects, as you heard just in the previous lecture, that come into play. And there can also be issues with how much nonlinear index change that you can actually get out of the material. In particular, you get saturation semiconductors, which are not in many ways true Kerr media because of the carrier density issues. Damage, that's a big one. There's a lot of work going on recently reassessing the optical damage in materials, how it comes about, its dependence on pulse duration, big field. In semiconductor materials, you've got issues with free carriers that are generated by highly intense pulses. Talked briefly about thermal effects as well before. So in terms of the sorts of materials that we've got to play with, this is a bit of a comparison table. Now, unfortunately, I didn't have time to go away and look at what's been going on in the polymer world most recently to compare with this. And there's also been some interesting work recently, particularly on silver-doped chalcogenide glasses that may exceed the numbers that we've got up here. This is what I've got for now anyway. So this is a table that's plotting some of the interesting features of nonlinear materials at 1550 nanometers. So we're talking nonlinear coefficient here, centimeters squared per watt. So you can see that a lot of these materials are all coming in at about the same number, with the exception of this one. This is a semiconductor optical amplifier we're talking about, which has an absolutely massive M2. Unfortunately, it has issues with carrier density effects that mean that it's a little harder to exploit that large nonlinearity. In terms of the figure of merit, you can see again these numbers over here. What's interesting here is these chalcogenide materials. They have huge figures of merit. Silicon, it's below that magic 1 number, which means that doing all optical switching in silicon, despite all the hoopla in the press, is actually quite hard. There are some things that you can do to avoid that, which is what a lot of that work's been based around, but nonetheless, that is a limiting factor for silicon. Another big issue is the dispersion of the material, because that's your phase matching condition. And again, you can see with the semiconductor amplifier, you pay a price for this number, it's got massive dispersion. And it's quite hard to engineer that out of a device. Silicon also has very high dispersion, but in nanowire devices you can engineer that down to 0. Chalcogenide materials have much lower dispersions that can be very easily engineered out. In terms of damage thresholds, much of a muchness. There are some questions about exactly where some of these chalcogenide materials lie. And the last thing we talked about here is the recovery time of the nonlinear effect. Now, in the semiconductors devices, this is all dominated by carrier effects. The intrinsic lifetime of carriers in a piece of silicon is actually even in the multiple nanosecond range. But by applying reverse bias to the device and making a multiple junction, you can actually start to suck the generated carriers out of the device. There's an interesting question as to just how far you can go with this. But my gut feeling is you're going to have a lot of trouble getting down into the few picosecond regime. Chalcogenides, on the other hand, because it's a purely electronic effect, we're talking only about how long it takes to move those electrons around. And there have been measurements that are talking down in the 20 femtosecond regime as the limit for this. But again, there are some interesting questions as to just how far you can go. So I'd like to call a break there, and we'll come back and talk about it later. Does anybody want to ask questions now?
Any questions for Steve now? Maybe I can ask a question. The largest nonlinear refractive index change that you can get in many materials is kind of seems to be fixed at 10 to the minus 4 or something like that.
10 to the 4, 10 to the minus 3, somewhere in that range, yeah.
Is that coincidence, or is there something deep lurking underneath?
I think a lot of it comes down to some of these higher order effects that you just start to excite higher order effects before you can get much higher. And whether there's any intrinsic material limitation, I haven't seen much said about that, to be frank. Don't know. It may. There's nothing around to suggest it's an intrinsic limitation, but it's not a widely studied phenomenon, I think.
All right. Let's take a small over time. We have 5 or 10 minutes.